This is the section on material balances when we have systems that have a reaction happening within the control volume. So this first lecture is on some very basic principles of information, such as limiting and excess reactants, fractional conversion, extent of reaction, chemical equilibrium, and so actually this, and this are going to be the second part of the second lecture of this. There's 2 lectures in this set. All right. And so the key is to be able to figure out everything that's going in and everything that's going out from the process. And so you want to be able to determine all of those materials, and we call these material balances, and these are reactive processes. So you all know basic stoichiometry. The general form for a stoichiometric reaction is we have stoichiometric coefficient times, which is a number of moles of a component, okay? And this is going to react and form products. So this new line here is written with absolute value bars because it will be, actually we understand this to be negative. There were no absolute value bars. The reactants would be negative and the products would be positive because the reactants are disappearing and the products are appearing. So this is an example of a chemical reaction. You may or may not be familiar with it, but you're actually doing this even as we speak, which is converting glucose and oxygen into CO2 and H2O and producing ATP, which is energy. And so we would write the stoichiometric coefficients for glucose. It's actually -1 because it's a reactant. This is phosphate, and it's -36. This is ADP, adenosine diphosphate, and that's going to we're going to add a phosphate to that, and that's going to be then available to donate phosphates where energy is necessary. So for O2 we have -6, but for CO2 we have +6, and H2O we have +6. So fractional conversion gives us an idea about how far the reaction has proceeded. If it may or may not go all the way to completion for different reasons. So the fractional conversion is written with the script F, and it's defined as the moles reacted divided by the moles fed of a particular component of the reaction. So we would look at specifically reactant A and calculate the fractional conversion of A, which is a reactant. And the moles reacted is simply the moles that were added minus the moles that come out or are present in the batch at the end of the reaction. And we divide that by moles in. So this is simple reaction, and all you have to do is look at the process stoichiometry and make the calculation. Or you can use this value to help you calculate moles out. So here's an example. If we feed 0.15 moles of reactant A and the conversion is 0.8, this time we know the conversion, and this is how much we fed, so now we can determine the moles out. And so in this case, the moles out is 0.03 moles. So most of it has reacted. I'm sure you remember limiting and excess reactants from Chem 1A or Chem 1B. Okay, and we will look at this calculation, and we're going to see the principles of limiting reactant, excess reactants, inerts, and also the process for determining these products. So here's a chemical reaction. We have sulfur dioxide combines with oxygen to form sulfur trioxide. So here's our composition of the gases going in, and the first thing to check is make sure that this all adds up to 1. It should add up to 1. And because all the mole fractions, oh, this is total moles, so never mind. Okay, so it does add up to 1. Okay, so assuming that we have 100% conversion of SO2 to SO3, we can look at the composition of the reactants and determine what are the excess reactants. And what we find is that the SO2 is limiting in this case, meaning that we cannot, if all the SO2 is converted, we will have no more SO2 present in the product. But we will have oxygen in the product because for 0.15 moles of SO2, which is what we have, we only need 0.075 moles of O2, and we have 0.2. So we have excess oxygen. And we can determine the amount of excess from the calculation of the moles fed minus the moles that are stoichiometric divided by the moles that are stoichiometric. And this will give you the fraction excess. Okay, are there any inerts? Yes. Nitrogen is an inert because we do not see it anywhere in the chemical reaction. So this is the actual reaction that takes place. And so now we can do the calculation of what we expect to find in the product stream. Okay. So the first thing we're going to do is choose a basis according to our problem statement. And given this information, this takes experience, but the basis most appropriate is to choose 1 mole of gas entering. Or you could choose 100 moles. And then this would be 15, 20, and 65. But if it's mole percent, then we have 0.15, 0.2, and 0.65. If you don't like decimals, then choose 100. And you can get rid of all those decimals. Okay, so we know how much SO2 enters. And if we know 80% of the SO2 is converted, then 80% of 0.15 moles, which is how much goes in, according to our basis of 1 mole, 80% of that 0.15 reacts, which is 0.12. So now we can write our actual chemical reaction as 0.12 moles of SO2 reacts with 0.06 moles of O2 and forms 0.12 moles of SO3. So starting, now we can take these pieces that we had to start with and subtract the amount reacted to get the amounts that are unreacted. So we started with 0.15 moles of SO2, subtract 0.12 SO2 and get 0.03 SO2. We start with 0.2 moles of O2, subtract 0.06 and we get 0.14. Of course, inert species do not participate in the reaction, so they leave the reactor as they entered. So if you can look at the outcome here, what we have left in our product is the unreacted reactants. We have an inert and we have a product. So the basic algorithm for determining the process stoichiometry is first draw a schematic of the process. Choose a basis. Sometimes the basis is already chosen. You may be told you need to look for a flow or flow rate. It may be in terms of total moles, or it may be in terms of moles per time. And then calculate the moles reacted using the stoichiometric relationship. And in doing this, you're going to calculate the excess unreacted amounts, and you're also going to determine the inerts. And finally, you can identify the product stream composition, the moles reacted plus the moles of reaction products, which also includes the inerts didn't react, so we include them in that group. So this kind of gives you the step-by-step process for how to do these calculations. So the first assignment is this quiz. Ammonia is reacted with oxygen to form nitric oxide. This is ammonia plus oxygen, forms nitric oxide and water. So here are the numbers. If ammonia is fed to a continuous reactor at a rate of 100 kilomoles of ammonia per hour, what O2 feed rate would correspond to 40% excess O2? Okay, so you can calculate that. Under those conditions, what is the flow of water in the product stream? What is the mole fraction of ammonia in the product stream? So go back to the previous slide, follow this schematic, this algorithm, okay? And your basis has already been chosen for you. This is the basis. This is what's being fed. Ammonia, 100 kilograms of ammonia is fed. So you can determine how much excess O2 do you have at 40%, and how much water, and finally look at the total collection of products and determine what is the mole fraction of NO in the product stream.